So the next talk will be by Subir Sachdev. It will be on a more different topic, quantum phase transitions of methods.
Okay, mic working? All right, so thank you very much, Ashwin, organizing this nice school. So let's see. So I'm going to begin by using the slides, but then I'll turn to the blackboard, at least for today's lecture. And there's a new version of my lecture notes, which are put on the website, I think, this morning. So everything I'm going to say is pretty much there. Many details of the calculations I won't be able to do on the board are all written up there. So, and if you have any comments on the lecture notes or my lectures, just please let me know. And please feel free to interrupt with questions as we go along. All right, so I thought I'd begin by just setting the stage and motivating the topics I'm going to talk about. And much of my work and also of many other people is motivated by this famous phase diagram, now going back over 30 years. So you might wonder why we're still working on it. Well, it's still the best superconductor, despite all the controversies and other things you may have heard. It's a very robust phenomenon, and there are many key questions that are still open. And also, there's been a lot of both theoretical and experimental developments in the last few years even. And that's the part I'm going to focus on. But don't worry, I'm going to start from the very basics and just talk about some important issues which have really only been clarified in recent years. So my focus here will be, as the title says, will be on metals. And what this phase diagram shows, I guess I have to look here. Yeah, now I can control it. What this phase diagram shows is that there seem to be three different types of metals here, as the shading seems to show. And I'm going to talk about all three at some level. And the details of precisely what these metals are, in particular what's happening here on the left-hand side, vary from compound to compound, not just in the cuprate superconductors I'm showing here, but the pnictides, and there are several other families of superconductors which involve strong correlations. And essentially all of them show this basic structure. But my interest will be mostly motivated by the cuprates, but a very general discussion could apply to many other correlated materials. Okay, so what are these three regions? So let me just introduce them. So first of all, of course, there's the ordinary metal on the right-hand side, meaning that's the part we understand, and that's mostly true. And that's mainly what I'll talk about today. So the ordinary metal is what we call a Fermi liquid. And a Fermi liquid is a state of matter which is adiabatically connected without a quantum phase transition to the free electron state. I mean, let's take that as a definition. So you start with free electrons, you write down its ground state, and then you slowly turn up the interactions. And as long as there is no quantum phase transition, you're in a phase of matter that we call a Fermi liquid. And I'll talk about its properties. And its Fermi surface is really the most important property that I'm going to focus on in these lectures. And that's the boundary, of course, between the occupied and the unoccupied states, which can be measured in photo emission experiments. All right, so that's one state. The other state, oops, I'm going the wrong way, is this famous pseudo gap. And there, as I mentioned already, things vary from compound to compound. But in the cuprates, we have this pseudo gap state, which has these Fermi arc type spectra. And I'll mention exactly what's going on, what we think is going on there in our approach. But much of my discussion will be much more general. It could apply to many other approaches. And the basic idea in the approach that I'm going to take is that the essential physics is of a quantum phase transition in a metal. So of course, at zero temperature, we're getting a superconductor, and that's good. And eventually, the theory can address that issue too. But we imagine that somehow, as theorists, we can turn off the superconductivity somehow, or in an experiment, you turn it off by applying a strong magnetic field. But that may introduce other phenomena that we may have to worry about. But theoretically, let's imagine that we could somehow turn off the superconductor. Then what we have set up is a quantum phase transition in a metal. So there's some quantum phase transition between the Fermi liquid and the pseudo gap. And that quantum phase transition is what's controlling the strange metal. And the superconductivity is something that just hides the basic phenomena. Of course, it's the most interesting phenomenon here, but we're going to ignore it in my lectures. So the superconductivity, for the most part, I'll mention it briefly, I think, once. Okay, so then, even though there is no actual quantum phase transition that you see here between two metals, that will be the theme of my talk, which will be quantum phase transition between two metals. So we have some tuning parameter here, S, which for the cuprate phase diagram is doping, but could be pressure, could be something else. And for S large, we have a familiar Fermi liquid. And as for S small, we have something else. Okay, and that something else could be different for different compounds. And because of this, then between this exotic metal and the ordinary metal, we have a quantum phase transition at S equals SC. And it's at this quantum critical point that's controlling at finite temperature the strange metal, at least that's the hypothesis. And also, if you really look at it more carefully, it has the seeds of its own destruction, and it just becomes, in fact, it's hidden by superconductivity. But that's the part that I won't say much about. All right, but we just want to understand different types of phase transitions that can occur in metals. Now, in all of the theory, so this has been studied for 25, 30 years, and I think there's a well-developed theory now, and there's several broad classes of these phase transitions, and all of them are associated with some scalar field. So in addition to considering the Fermi surface, we also have to consider a boson, which I'll call phi. And this boson has one phase where its expectation value of 0, and the other phase is expectation value of non-zero. Now, if this boson is an ordinary autoparameter, then this phase breaks a symmetry, but that's not essential. This boson could be a Higgs boson. It could carry some gauge charges, in which case this would be a Higgs phase, and this would be a phase where there's no broken symmetry. So there would be a quantum phase transition, which would be some kind of Higgs transition, where the Higgs condensate turns on. But the useful thing about studying metals is that even though a Higgs transition could be rather subtle, especially if it's not breaking any symmetry, here it's not subtle at all. The presence of the Higgs condensate changes the Fermi surface. And so you can see this directly in experiments. All right. So this is what I'll talk about today's lecture, various cases, if I get there, of Fermi surfaces coupled to various scalar field and how they describe different types of phase transitions in metals. All right. So this has been studied a lot, and in 2 dimensions, the different cases are pretty well understood today, I would say. And the cases that I'll talk about are things like various order parameters, Ising nematic spin density wave, or Higgs boson, as I've already mentioned. So this is all, by the end of these lectures, you'll know all of these cases fairly well. Okay, so, right, what's next? Yes, so what has been learned is in 2 dimensions, 2 spatial dimensions would be exclusive focus on my lectures. 1D, none of this applies. In 3D, it kind of applies, but this last statement, not necessarily. This critical point is not as subtle as it in 2 dimensions. And in particular, what you find in 2 dimensions is that the basic structure of a metallic state, that it has well-defined quasiparticles, breaks down at this critical point, and you have a metal without any quasiparticle excitations. Okay, so now a common hope, and in fact more than a hope, a claim in many, many papers by famous people, is that this entangled non-Fermi liquid state, once you understand this state, and you go to finite temperature, you're going to get the strange metal that's seen in experiments. So, this is the reason everyone's been studying this so hard, because maybe it will help understand the strange metal phase, and then that would be a precursor to understanding TC. If you're going to understand where superconductivity onsets, you have to begin understanding what's the other phase on above TC. So that's been the hope for a lot of work and many explicit claims. They never really quite worked out because there wasn't any clear-cut agreement with experiments, and this has been the focus of a lot of study, though. But the answer we know today, and this is the recent work by a variety of people mentioned here, is that the answer is no. So in fact, the motivation for a lot of work in this field for several decades overlooked some simple things, well, in retrospect, simple. And once we account for them carefully, we find that at least in the problem as defined of quantum phase transitions associated with this kind of non-Fermi liquid state without disorder do not have, in fact, a strange metal. They have a perfect metal, meaning that, in fact, in some idealized limit, the resistance is zero. It's not large, and it's not linear function of temperature, as we'll talk about. So what is the answer? So there's been, again, a lot of progress. Of course, I've set this up so that by the end of the lecture, I'll give you the answer. And the answer is we have to include spatial disorder. You can't consider a translationally invariant system. You have to talk about breaking of translational symmetry by impurities. Now, that shouldn't be as shocking as it seems. Even the theory of metals, ordinary metal like copper, to understand its transport properties, you can't just ignore the impurities. In fact, impurities control the resistivity of copper. Now, what happens in metals, ordinary metals, is that the effect of impurities is controlled by something people call Matheson's law. That is, you can imagine the electrons scatter off each other, and that gives you the inelastic scattering rate. And they scatter off impurities, that gives you the elastic scattering rate. You just add them up, and so you can solve one without worrying about the other. That's not true at such quantum phase transitions. You do really have to do the whole thing self-consistently. You can't just take the impurities and take the interactions and treat them separately. So that's kind of where I want to go and show that spatial disorder in the position of the QCP, meaning that this portion of the sample has S greater than SC, this portion has S smaller than SC. That's invariably what happens in a real system. And once you include the effects of that, and there's been a lot of progress in the last few years, and there's still ongoing work, but it seems very promising that you do get some kind of strange metal. You do get a strange metal. Whether this is a complete explanation of the experiments, well, let's see. That's still a work in progress. Okay, so that's it for the slides. So I'm going to start at the very beginning now and talk about the Fermi liquid state. Any questions before I turn to the blackboard? Okay, let's see. All right, so these notes are on the web. They're actually extracted from my book, and but I printed them out, so you don't have to buy my book, but doesn't mean you shouldn't. Okay. So I'll try to write big. So let's see, Fermi liquid or ordinary metal. So let me just, I think most of you have probably seen this in your courses, so I'm going to be fairly quick, but just highlight a few properties that'll be important for our discussion. And there are many of the detailed calculations are in the notes, at least some of them. So you can. So what is a Fermi liquid? Well, as I've already stated, it's a state of matter that's smoothly connected without a quantum phase transition to free electrons. So the ground state connects to the ground state. But we also maintain, and this is verified by explicit calculations, that the structure of the excitations is also very similar. And so what is the basic structure of excitations in a free electron gas? Well, you have what's called a Fermi surface, which separates the occupied states and the unoccupied state. This is in momentum space. Okay, this need not be a circle, but okay, let's draw a circle. And the excitations are the following. In this, I'm working now in the grand canonical ensemble. The excitations are holes inside the Fermi surface and electrons outside the Fermi surface. And these hole-like and electron-like excitations have an energy that vanishes on the Fermi surface. So excitation energy, E sub k of these excitations goes to 0. So of course, by definition, all the excitation energies have to be positive. But if you think that way, then you have to keep track of what's a hole and what's an electron, and it becomes rather complicated. So the way we do it is we set it up so that negative energies talk about holes and positive energies talk about electrons, and then we only keep track of a single distribution function. So I'll talk about that in a minute. Anyway, so in any case, the physical definition of a Fermi liquid is that this is also true in an interacting electron gas, that there is a surface of codimension 1, so it's a circle in 2 dimension, where the excitation energy vanishes. So this is almost immediately something much more singular that happens in any quantum field theory you're about to meet, in any book on quantum field theory, because there the excitation energy vanishes only at a point in momentum space, 0 momentum typically, or a discrete set of points. And it's rare that you have such a large set of low energy excitations. Typically, you would think if you have so many low energy excitations, the phase is unstable. It'll do something else. And that's actually true. It is a superconductor or a spin density wave or a charge density wave. There is something called the cone-Luttinger instability. So it is always unstable to superconductivity, at least, except in a few exceptional cases. So but we're going to ignore that and just treat it as essentially a stable phase of matter, where the excitation energy vanishes on a surface. And this is probably also the reason, just to refer to the previous talk, that there hasn't been any, as far as I know, successful treatment of Fermi liquids or Fermi surfaces with tensor network methods. Those really seem to describe a whole different class of correlated states. We have to somehow marry those two approaches, I think, and that's something I'll talk about probably in the next lecture. How do you get more complicated many-body states with Fermi surfaces? Okay, so how do you talk about such a state with the pole-like and electron-like excitations? Well, so these excitations we're going to call quasiparticles, although they're not just simple single electron or single hole. They're an electron or a hole with a cloud around it. And to not have to worry about what's a hole and what's an electron, what you say is that in the ground state, you write down as a function of momentum, n cube quasiparticle in the ground state. You just postulate that you think of the ground state. Let me get the same notation that I have in the notes, sorry. N0 of P. Okay, this is N0 of P. So this should be P. So the ground state, we say, has the same distribution function of quasiparticles that the free electron gas has of electrons. So this is 1 over here below the Fermi wave vector and 0 above it. Now, it's not true that you could just take the quasiparticle wave function and write out the ground state in terms of this distribution function. In fact, the quasiparticles well below the Fermi surface are not even well defined, but we just postulate this as a tool to be able to treat electrons and holes in the same way. in the end, we'll only be looking at changes in this near the Fermi surface and very small changes over there. And so therefore, we'll be limiting ourselves to momenta where, in fact, this description of quasiparticles is valid. So let's see. So you have some distribution of actual quasiparticle in some excited state. There'll be some n of p. And we're going to say that looks like this. So that's n of p. And then this density of quasiparticles, delta n of p, will be n of p minus n0 of p. Okay, so then what is the energy of some excited state? So the basic structure of a Fermi liquid, they can take some many-body state and approximately compute this energy by just knowing delta n of p. So in fact, delta n of p describes completely my quantum state. So this is also a very radical claim because many-body wave function has an exponentially large number of components, whereas this is a function only of one parameter, p, and we claim it's sufficient to talk about the properties of a complicated many-body state. And that's something that's justified a posteriori, and really is the statement that these quasiparticles near the Fermi surface are approximately non-interacting. At least they live a long time, and you can think of a many-body state as just made up of some set of quasiparticle excitations. So if you look at the energy, or even the free energy, well, let's talk about the energy, it's some functional of delta n of p. And this is called the Landau functional. And for non-interacting electrons, this is obviously given by just you take the dispersion of the electrons and you multiply it by delta n of p. Okay. And this gives you the energy of some excited state, which is characterized by some distribution of quasiparticles delta n of p. Now, so this, and where you might say that this E of p is some renormalized energy, say it's p squared over 2m star. Okay. And the effect of the electron-electron interaction is to renormalize, sorry, it can't be that. It's p minus pf modulus over m star. So we're talking about energies that vanish on the Fermi level, kf. So you might think the only effect of the electron-electron interaction that we need to keep track of is this m star. And once you replace m by m star, you have then a good description of an interacting electron gas. So what Landau pointed out, but that's not quite correct. There's another term which is of the same order as this term. So the point is the following. So this delta n of p, is non-zero over some region. We'll think of that as the temperature. There's some energy, momentum or energy range of order temperature, over which delta n of p is non-zero, where the ground state quasiparticle distribution function and the excited state quasiparticle distribution function differ. So you get a factor of t from the fact that this is of order t, is non-zero over width of momenta of order t. But the energy itself over which you're excited is also of order t, because, well, it vanishes on the Fermi energy, and this width is of order t. So this whole thing here at temperature T is of order T squared, because both quantities are small. So what Landau pointed out was that you have to include another term, which is also of order T squared. I guess I'll write it down over here. And that's the Landau interaction term, which I can write in the following way, is 1 over 2V and these coefficients here are the Landau interaction parameters. Okay, so the point here, of course, being delta n is of order when you do the integral over P, delta n of P is about a temperature. So you take two factors of delta n of P and delta n of K. This whole thing will also be about a T squared, where these interaction parameters are about a 1. So these are about a 1. And this also have to be accounted for. So this is something, it's a new term that's present for the Fermi liquid, not present for the free electron gas. And it does lead to some changes in physical properties. But it's a finite set of numbers. If you have some symmetries, you can reduce this function to a few numbers that you need to characterize an interacting Fermi liquid in addition to the effective mass. All right. Okay. So the other thing to note here is that this is a purely classical type term. It's a density term. So it seems, something rather singular. If you write down some interaction term in terms of electrons, you would say, C dagger P, C dagger K, Cp plus Q, Ck minus Q. This is what the general interaction term looks like. Whereas if you look at this, it's something like C dagger P, Cp, P dagger K, Ck. It's just a secular shift in the energy. It only involves the diagonal terms where Q is 0. And naively, you might think that this is really a very singular term because Q equals 0 is a contribution of order 1 over the volume. And so why should this matter? Well, the point is that you can think of this as just the energy of a single quasiparticle shifts a bit from the energy of all the other quasiparticles that might be excited, and that's what you're accounting for here. There's no real scattering. This is just, this term leads to scattering and lifetime of quasiparticles if you think about it more carefully, but this term is just a secular shift in the energy of every excitation. All right. So that also then introduces the next thing we have to verify, that the lifetime of the quasiparticle is very long. So quasiparticle lifetime. You can try to compute this in diagrams, and it leads to a very horribly complicated mess. Easiest thing to do is to use Fermi's golden rule. So you imagine you have some particle here, and it's going to scatter some particle that's occupied inside the Fermi surface. So this has momentum P, this has momentum K, and this is going to scatter to P plus Q, which is an empty state. And this K is going to scatter also to an empty state, which is K minus Q. So if this process is happening, then you apply Fermi's golden rule, and you say that 1 over T, tau is someone, so the particle is someone K and Q of some matrix element squared. But the most important thing is to keep track of the fact that there's Fermi's exclusion principle. So the state that you scattered off of should be occupied. Let me draw another picture here. So you have a particle coming in, P, you have another particle with K, and that's scattering off into K minus Q and P plus Q. So there's f of K, and then the other two must be empty. 1 minus f of E K minus Q times 1 minus f of E P plus Q. Okay, so now you have to do this rather complicated integral of momenta to figure out the scattering rate. That's in general extremely complicated. But to get a first guess, you just ignore the momentum dependence of this. And you also rewrite everything as energy integrals using the density of states, because everything is dominated by what's happening near the Fermi surface. So this thing can be reduced to an integral. This becomes something like integral over, oh, sorry. Most importantly, I forgot about energy conservation. So this process must conserve energy. So EP plus EK must be EP minus Q, EP plus Q minus EK plus Q, K minus Q. Sorry, this can't possibly be legible. I'm sorry. It hasn't been cleaned properly. All right, so let me continue over here. So if you can convert that to an integral over energies, dE1, dE2, dE3 of f of E1, 1 minus f of E2 times 1 minus f of E3, and momentum conservation, delta of E plus E1 minus E2 minus E3. Sorry, that's energy conservation. Ignoring this T squared momentum dependence of the scattering matrix element, and also taking all the integrals near the Fermi surface, where you can use the density of states to convert it to an integral over energy. Okay, so this is an integral that you can do exactly. And this thing basically goes as, roughly speaking, max of temperature squared or epsilon squared. So the point is that the scattering rate vanishes on the Fermi energy, where if you're sitting exactly at the Fermi energy, where epsilon is 0, it vanishes as temperature squared. And so the lifetime of the inverse lifetime is of order t squared, whereas the energy is of order t. And so because this is much, much smaller than E or t, they're roughly of the same order, the whole procedure is self-consistent. That the scattering processes can be neglected, and you only need to account for a secular shift in the quasiparticle energy from the presence of other quasiparticle of finite density. If there's only one quasiparticle, this won't have any effect. If there's other quasiparticle at finite density, that will change the energy of the quasiparticle you're looking at. Okay, any questions? Yes. I'm not. The moment that you can do it, so if you do that, there are a few cases where you can do this integral with momentum conservation. Then you find you still get this, but it changes the coefficient in 2 dimensions and higher. Actually, in 2D, you sometimes get log corrections, but that's fine. There's still a t squared. In 1D, this breaks down when you account for momentum conservation. Doesn't work in 1D if you accounted for momentum conservation. Okay. All right, so let me make a few more remarks and then get to some other topics. So this tells us something about the structure of the Green's function of an electron in a Fermi liquid. So it has a very long lifetime. And so I can write the Green's function in the following manner. Okay. All right. So in general, the Green's and all the details of all the analytic structure is in the notes. You have some Green's function, the function of momentum, and some frequency, some complex frequency z, and this I can write as z minus EP minus a self energy, which is a function of p and z. So this is a very general expression. So what we can say now is that in a Fermi liquid, for p close to pf, what happens is that the Green's function, and I'm going to write it now as with Matsubara frequency I omega, is some term like this, Zp over I omega minus Ep plus I gamma p sine omega, plus another term which is called the incoherent contribution. Okay, So what is this structure telling you? So when in a free Fermi system, gamma p is 0. And so then you have a pole when z is about an EP. Now, in an interacting Fermi system, because of the presence of, because the lifetime is so long, this gamma p is basically the inverse lifetime. So gamma p is very small. You have a pole that's just off the real axis. So to make it a little more precise, if you look at the complex frequency plane, so this is the z plane. And you look at the pole, so I'm going to look at this in, and this is important actually, in the second Riemann sheet. The physical Green's function, has a branch cut on the real axis. So if you look at the Green's function, the physical Green's function defined by the usual time order prescription, it has a branch cut on the real axis. And above the real axis, this is the retarded Green's function. And below the real axis, it's the advanced Green's function. And none of these quantities have poles. They're actually completely analytic. However, if you take the retarded Green's function and analytically continue it behind the branch cut, that is, you go into the second Riemann sheet, you do find poles. Okay, so the retarded Green's function, G R of Z, is, well, you basically take I omega in the upper half plane. So this becomes positive. So that becomes basically Z minus EP plus I gamma P. And now this function, this is only defined in the upper half plane. In the upper half plane, this doesn't have any poles. However, if you analytically continue in the lower half plane, it has a pole at Z equals EP minus I gamma. So if you take the actual interacting Green's function of a strongly interacting Fermi liquid, it has a pole in the second Riemann sheet, and it's somewhere off the real axis. And then you ask, how does this pole move as a function of momentum? So this is at t equals 0. So the pole is here. It does something like this. So this is as a function of momentum. As momentum changes, it moves this way. And this at this point is P equals PF. So right at the Fermi level, the pole hits the real axis. The quasiparticles are infinitely long-lived. But away from the Fermi level, if you go below the Fermi level, there's a finite lifetime, and also above the Fermi level. But the important point is this is quadratic. This is a parabola. The reason this is a parabola is precisely because of that E squared over there. And so this tells us that the imaginary part is always much smaller than the real part. And so these are the quasiparticles that exist near the Fermi surface. All right. Okay, so this also allows us to give us a very precise definition of the Fermi level. So what is the Fermi level? Well, the Fermi level is basically the point where this pole is present. So when the pole is present, of course, this term will dominate that. So you don't have to worry about that. So you just look at the inverse Green's function. So G inverse of P equals PF, Z equals 0 defines the Fermi surface. So you say you have some numerical way of computing the Green's function as a function of momentum at 0 frequency. Well, you have to compute the inverse Green's function and find the locus of point where this equation is satisfied. And that gives you exactly where the Fermi level is. Okay, and so on. All right. You can also take this form and write down, what the physical electron distribution looks like in a Fermi liquid. So let me also say what that is. So if you look at N of P, this is the actual electron distribution, and E of P, which is expectationally of C dagger P CP. So this comes from a Fourier transform of this. So this is close to 1 at 0 momentum, and here's PF. So this thing has a discontinuity at the Fermi level. And this discontinuity is precisely this residue Z of PF. Okay. So these are things that can be established to all orders in perturbation theory, that the Green's function has this structure. There is, in fact, indeed a solution to this equation over here that defines the Fermi surface. The poles near the Fermi surface have this structure, and the momentum distribution function has a discontinuity in momentum at PF due to the presence of these zero energy excitations. Okay, so those are things you can establish in your favorite theory by analytic computation, usually perturbation theory, and that defines what a Fermi liquid is. Okay. All right, so this state of matter that I've defined now has one very remarkable property that I haven't mentioned yet, and that's the Luttinger relation. So that's what I want to talk about now. There's a question? Yes. Is it what? Analytic? Yes, it is. So it's analytic everywhere off the real axis. It has a branch cut on the real axis. You take the time-ordered Green's function, the only singularity is a branch cut on the real axis. But if you take the function in the upper half plane and analytically continue it into the lower half plane through the branch cut, then you see the poles. Yeah. Yeah. Well, I mean, there's a finite jump for a Fermi liquid. Yeah, so the discontinuity is a measure of the density of states, and that's finite at the Fermi level. Yeah. Well, it's something you can deduce from this. You look at this function and know that gamma p goes as p minus pf squared, epsilon p goes as p minus pf. You plot this up, and you'll figure out what it is. Okay. Yeah. So you can also use this expression on the real axis. So there's a finite, I mean, because this is a Lorentzian, there's a discontinuity. However, there is a pole. There is a pole at one point, which is right here. This point, there is a pole. So everywhere else, it's a branch cut. Yeah. No, the Landau parameter is not anywhere here. And that comes in when you look at, say, spin density or electron density correlation functions. Then that's a new parameter that comes in. It's not something that's defined by just the Green's function. M star is defined from here. So if you take the real part of the self-energy and the actual quasi-particle dispersion, epsilon quasi-particle is basically EP plus the real part of sigma of P and 0. That gives you M star. Well, not quite. Okay, there's also some renormalization from the self-energy of the coefficient of I omega that goes into Z. Yeah, so it gives you some ratio of Z over M star. Okay, yeah. This is all in 2 or higher dimensions.
We know in 1 this
does not work because gamma p is not so small. This breaks down. So gamma p is in fact of order t. It's not of order t squared. And so you have to do something else entirely. So the important thing is that the imaginary part of this curve is smaller than the real part. Yeah. Yeah, no, it cannot give us what this is. Right, so this is just giving you the dispersion of one quasiparticle. The Green's function knows only about one. You start with the ground state, it's a zero temperature, about one quasiparticle. It's talking about its properties. Now, if you take a finite density of quasiparticles, then that's when the Landau parameter comes in. So you need the total energy of the system, this energy E of delta n, that's extensive. It's a part of the volume of the system. And that's when the energy is extensive, then this comes in. Yeah.
So I think of the fact that if I instead continue the advanced, then I would have these folds.
Sure, yeah, that's also true. There are two sheets, and usually we work with the retarded Green's function because that's the one. I mean, you could do everything with it advanced too, but the retarded Green's function is what's related to the Kubo formula, at least in all the textbooks. So we just work with that. All right, so then the other most remarkable property of the Fermi liquid that I want to mention is the Luttinger relation. So today we understand the Luttinger relation as yet another example of an anomaly, I guess, or some type of anomaly, as Oshikawa first argued. And I think he's going to talk about this next week, I believe, from the title of his talk. So there's a modern way of understanding the Luttinger relation. And it's very important because it's a non-perturbative argument. And it also allows you to talk about what happens to this relation in more complicated states. Here I'm talking about the simplest possible many-body state of fermions, which is a Fermi liquid. There are, this is understood in the 60s, and it was a kind of piece of 21st century physics that was discovered in the 1960s. And as time goes along, we are understanding it better and better. But I'm just going to give the old 60s argument here, and maybe later in my lecture, I'll give a portion of my lecture I call Oshikawa for Dummies, where I'll talk about how this generalizes in more complicated states. But I think Misaki will say more of the subtle topological aspects of it next week. All right, so what is the Luttinger relation? So the Luttinger relation is a statement that the volume enclosed by the Fermi surface, so you define a Fermi surface this way, and then, so you solve that equation. So, you determine the Green's function, you solve this equation. That gives you some curve in momentum space, kx and ky, in 2 dimensions, gives you some curve. And if imagine you do this for a system at fixed density, and you start with the free electron problem. And the free electron problem is trivial. We know we can determine this curve. And then you turn on interactions. And what Luttinger showed was that the area enclosed by this area, by this curve, is independent of interactions. That is, if you turn on the interactions to all orders in perturbation theory in the interaction, we can prove, this is what was proven in the early days. So it's a perturbative proof, ultimately. As much as they may claim in the books it's not, it is. And it doesn't change. So some kind of topological invariant. The shape can change. The shape can change as you turn up the interactions. But as long as the density is fixed, now the area enclosed by this locus of zero energy excitation by solving this equation doesn't change. All right, so that's the Luttinger relation. And hence the importance on the Fermi surface, really, because this is something, the nice thing about the Fermi surface is not only a topological property, you can measure it. So there's infinite numbers of measurements of Fermi surfaces, like I showed you. And so you can immediately check. And in fact, in this high doping region, where I said you have an ordinary metal, people have indeed checked this works. You can measure the Fermi surface, you know the density by other means, and see that they exactly correspond to each other. All right, so there is kind of a proof in the lecture notes. I'll just quickly highlight a few points from it, and that's really all I'm going to say about Fermi liquids. Okay. Okay. All right, so how does the proof work? So the proof is you start out with an expression for the electron density. Sum 1p minus 1 over p. And I'm going to go from minus at 0 temperature, d omega over 2 pi, g of p and omega, e to the I omega 0 plus. 0 plus means that's a positive infinitesimal. This is needed to time order the Green's function in the correct way so that you get the electron density. So this is the quantity that we're going to compute for this Green's function. So we have a very complicated Green's function with some complicated self-energy. It has this pole structure that we know about. And somehow, remarkably, we can say something exactly about this without knowing anything more about the Green's function. Okay, so how does the proof proceed? Well, first of all, you just use a very simple identity to write this thing as this quantity here as I d by d omega minus I g d sigma d omega. Okay, so you can just verify this is correct by taking log of that expression over there, and just simple algebra tells you you just get a g. All right. So this is a very nice way to write it. Why? Well, one, there's a term here which vanishes for free electrons. So because sigma is 0, so we know whatever happens for free electrons, if we know how to compute, we can just compute from here. And two, this part here is exact derivative, so we have some hope of evaluating it. We can just, integral over omega, you have d by d omega, maybe we can evaluate it. Okay. So what happens here in a Fermi liquid, that these two terms have the following fate. So this thing is the same as for free electrons. Okay. And this thing turns out to equal 0, even for interacting electrons in general, once you do the integral of momentum and frequency. All right, so those are the two ingredients in the proof. So this part I'm going to leave for you. It involves some hairy, complex analysis of doing contour integration with this structure. But it's very simple in the end because it's a total derivative. So how difficult could it be? Okay, so you find that this is equal to, in the end, just sum on p theta of minus EP. Sort of, where EP is this EP, including the real part of the self-energy. The full self-energy, EQP. Okay. And that seems rather plausible because the imaginary part vanishes at this point, and that's the point where the real part also vanishes. So if you just do the integral and distort contours, you get exactly the free particle answer. All right, so that's something, doesn't require any special physical insight. It's just requires some expertise in complex analysis, which I don't have. So you just have to read the notes. All right. So on a good day, anybody could do that. But this is kind of surprising. Why is this true? Why is this also 0 for the case of interacting Fermi liquid? Okay, and that's really the non-trivial part. So I'll try to give the argument here. It's an argument. So what you find is that this thing is zero due to a conservation law. So this is a interacting fermion system with a conserved electron density. So it has a U1 global symmetry. So the vanishing of this is in fact closely associated to the presence of this global U1 symmetry. And that's what's explained in the notes. All right, so let me try to at least sketch that argument now. So we want to look at sum on P, sum on d omega, sigma, what is it? G d sigma d omega. Okay, so there's two steps in this argument. One is that there exists a functional called the Luttinger functional, so of G. So there is such a functional, okay, which involves the exact Green's function G. So you give me an exact Green's function, I'll give you a number. That's what I need the whole function, which depends on both P and omega. You give me a Green's function, and I'll give you a number, and that's the Luttinger functional. So this is something you can prove exists, again, by Feynman diagrams, one of those fancy Feynman diagram things. You draw lots of diagrams, and you write down skeleton diagrams, and you establish that there is some expansion for this Luttinger functional to all orders in the interaction. All right, such a functional exists with the property that the self-energy is the variational derivative of the Green's function. Okay, so given the Green's function and knowing the Luttinger functional, which are all big ifs, you don't really know those things. But if you know those, you could then also deduce the self-energy by taking a derivative of the Luttinger functional. All right, so now we can insert this in here. And then you see something neat. So if you're very sloppy, this is G d by d omega of delta phi delta G. So you can see that's d by d omega of phi, basically d by d omega, of log of phi, right? Yeah. Okay, I've forgotten now. All right, so it's log of, no. D by d omega is d phi dg. So you have to first integrate by parts. Okay, so if I'm very sloppy, you integrate by parts, you write that sigma dg d omega. So that's the same as delta phi delta g dg d omega, and that's the same as d by d omega of phi. And so now you just have to, now you can do the omega integrals and prove this thing is zero. Okay, that's extremely sloppy, but that is what goes on in the textbooks. But let me try to make it a little bit more precise. So the Luttinger functional has the following property. So this is really the way you should prove this. So phi is a function of G of P and omega. So the statement is that if you take phi of G of P and I omega, and you shift it by some frequency omega 0. So you give me a G of P and omega, I give you another function, which is the same function shifted by some omega 0. Now the Luttinger function has the property that this is independent of the shift. And this follows from U1 global symmetry. Which is that if you can C e to the I pi theta is the symmetry of the action. So in fact, what you do is to prove this, what you do is, and this is discussed in the notes, so I'll leave it for you to read there. You imagine that this is time dependent. So you weakly gauge a global symmetry. So now, of course, the action is not invariant under a time dependent theta, but it changes in some very simple way. And from examining how it changes under this time dependent gauge transformation, you can then argue modulo certain issues of branch cuts that you can ignore, which turns out to be correct for the Luttinger functional, that you can, this identity is true. Okay. And now so this is the more correct way of doing it. And it also establishes the close connection to a U1 global symmetry. So the way Masaki is going to prove it is, in fact, in his argument too, there's kind of a gauging of a global symmetry. It's some kind of mixed anomaly between the global U1 symmetry and translational symmetry, which is implicit here, because even the concept of a Fermi surface requires conservation of momentum, at least the way I've defined it. Yeah. All right, so the algebra of that is in the notes, but I don't think I can reproduce it up here, but you can read about it. Yes? For the what? I can't hear. Not that I know of. No, it's just only for U1. And there's no such thing for non-abelian symmetries either. It's special for U1. I mean, in fact, this anomaly and this is also present for boson systems. So in principle, if you had a boson system whose ground state did not break any symmetry, in particular did not break the U1 symmetry, it would also have a relation like this. Bosons also must satisfy a Luttinger relation. And that's, of course, very much connected to many things. Spin systems we know are sort of boson systems, and they're bosons at half filling, and they have all kinds of anomalies which are essentially the same, connected to this anomaly. All right. Okay, so that's what I have to say about Fermi liquids. Hopefully you've heard a few things you haven't heard before. And any final questions before I go on to the next topic? All right, so I have 10 minutes more. Much slower than I thought. Okay, all right. Okay, so we've got a Fermi liquid. The next thing we have to do is add a quantum phase transition. And so let me begin with the Ising model of quantum phase transitions, and then discuss how the quantum phase transition would change in the presence of a Fermi surface. I don't think I'll get that far, but let me just get as far as I can. Okay. Okay, so this is, you take the following Hamiltonian, and this is true in any dimension, but I'll focus on two. You have a bunch of qubits on a lattice, and you have, say, a nearest neighbor coupling, Zi, Zj, between the qubits, and a transverse field I'm going to call H. Actually, I call it G in the note, so let me call it G, because G will later on become something else, some on I, Xi. So this is the Ising model in a transverse field. If the Xi wasn't there, this is a classical model, and the ground state is a ferromagnet. Now this Hamiltonian has a Z goes to minus Z symmetry. So there's the ground state is all spins up or all spins down. Now that symmetry is still preserved by the extra operator, so the Z2 symmetry is still there. And so what happens as you turn up G is the following. So as a function of G, in any dimension, there's a critical point GC. So for G less than GC, there's a broken symmetry, and Z sub I is not equal to 0. There's a broken Z2 symmetry, and this can be all plus up or down. And on this side, Z is 0, and that's the non-ferromagnetic phase. All right, so there's a quantum phase transition, which, this is an unfrustrated model, and then I think on just about any lattice, it's a continuous phase transition. In one dimension, I think maybe Shuang is going to say much more about this model. So this is a conformal field theory with all kinds of interesting duality properties. My focus here is on 2 dimensions, where it's still a conformal field theory. And it's a strongly interacting conformal field theory in 2 + 1 dimension. In some ways, it's the basic model of a non-trivial conformal field theory in higher dimensions. And more is known about it, although not everything. And in 3 dimensions, it becomes kind of like a free field, mean field behavior with log corrections and so on. So the focus here is on 2 dimensions and not on the exactly solvable CFT in 1 dimension. All right. What was I? Okay, yeah, so let's talk about D equals 2. So D equals 2 has also another very interesting property. So we meet these 2 ground states, and we can now ask, what are the excitations? So this system resembles the system, the phase diagram I showed, in the sense that on either side of the critical point, the excitations are very simple. They're quasiparticles. In this case, the quasiparticles actually have an infinite lifetime. So they're even better Fermi liquids than Fermi liquids. And the reason is that the quasiparticles have a gap. So what happens over here? Well, here the ground state has all spins up. And the quasiparticle, say, is 1 flip spin or some set of flip spins. It could be 2, let's say. I don't know, it depends on the details. So here's a little bubble of downspins, and that's my quasiparticle. Now, one can show that there's a finite energy gap. So it's much better than Fermi liquid, where the energy gap of the quasiparticle vanished on the Fermi surface. Here, it doesn't vanish at any momenta. And therefore, if you create one quasiparticle, well, there's nothing it can do. It lives forever. On the other hand, for a Fermi liquid, it lives forever only on the Fermi surface. Here, it lives forever for a whole range of momenta, a finite range of momenta. And in fact, the only point where the particle can decay is if you give it enough energy to create 3 more quasiparticles. So you have a quasiparticle here. It can, through interaction, it can get 3 particles. So this has some energy gap. So this has minimum energy delta. Each 3 of them has energy delta. So this process can only continue if this thing had energy 3 delta. So as long as the excitation energy is smaller than 3 delta, the lifetime is infinite. Okay, so the quasiparticles are extremely well defined on this side. And similarly, on this side too, they're extremely well defined. And all of this you can show by perturbation theory, either in G on this side or 1 over G on this side. And the notes have some discussion of the nature of this perturbation theory. Typically, I give a whole bunch of homework problems, some of you may have done, on computing these things. So on this side, every spin is pointing to the right. But there's a quasiparticle of a flipped spin. So this thing is your quasiparticle, generally 1 flip spin, but as you look, and this also has some energy gap, energy bigger than some gap delta. Okay, so that's great. All of this you can show by for G very small or G very large. The whole question is what happens as these 2 states of matter, each of which have quasiparticles, meet. But the important point, of course, is the quasiparticles here are very, very different from the quasiparticles here. They have a very different structure. One has a broken symmetry, the other doesn't. So they can't just smoothly connect to each other. In fact, the ground state can't connect, so neither can the excited states. So there's got to be at least one quantum phase transition. Now, it could be some first-order transition where the state just changes from that to that. Well, then that's boring from our point of view. But it could also be a continuous phase transition. So what could happen is that the energy gap as a function of G, vanishes at some point, Gc. So this is the energy to create one quasiparticle, and it vanishes at one point, and that's the point we want to study. All right, so that opens a problem. How are we going to describe this phase transition between two very different types of states of matter and two different sets of quasiparticles? And do the quasiparticles survive at this one point? Okay, so this is where quantum field theory comes in. So it's quantum field theory to the rescue. It's an approach that allows you to go from one side to the other. You can't use perturbation theory in G or 1 over G anymore. So the idea of quantum field theory is kind of based on universality. And let me try to just sketch that. So the claim is I'm going to now write down a quantum model which has the same basic properties over here and here. They completely match. And then I'm going to appeal to universality to say that, well, actually, it also describes what happens near GC. Okay, so the model I'm going to write down is the following model. It's a bunch of coupled nonlinear oscillators. So I take the following Hamiltonian. H is 1 over 2m pi phi squared, so plus some v of phi. So I have a bunch of some oscillators on each side I, and they're coupled together by the same J, phi I, phi J. So this is the conjugate momentum to phi. And what does v of phi look like? Well, it looks something like this as a function of phi. And this is phi equals 0. So rather than considering the Ising model, I consider a bunch of coupled nonlinear oscillators. All right, so now, roughly speaking, I can say that, if this potential is very deep, there are two states. There's one state here, which is the even state, and there's an odd state with some small energy splitting, which I'm going to call G. Is it G? Or is 1 over G? Well, let me not call it a delta in the notes, okay. And I can think of this state as the spin pointing to the right, and this state as the spin pointing to the left. So for a certain V of phi, it seems the low energy spectrum over here has the same kind of low energy states that you would get from the transverse field term, which I have now erased. Okay, but really ultimately, and so then you couple them together, and maybe at some point, as J becomes large, it will have a phase transition into the ordered ferromagnet. Now this model, as written down, we can imagine, taking some continuum limit. That's the nice thing about scalar fields. We can, rather than spins, which are hard to work with in the continuum limit, we can imagine the fluctuations of phi are weak and take some continuum limit. So in the continuum limit, I can write down the following field theory. So I'm going to write down now a continuum field theory, d dx. And let me also go to time. So this is the action. It will be d phi d tau squared plus grad phi squared plus s phi squared plus u phi to the fourth. So if I look at this theory, then for s less than 0, the potential that the phi sees is something like this. So if, now I'm just a 5-foot field theory, so I can imagine that I'm going to get a ground state is going to be either here or here. So this is a ferromagnet. It's going to be either here or here. And for s greater than 0, I'll have a potential like this. All right, so now I claim, you have two ground states here, which have the same structure for the Ising model as for this 5-foot field theory. Sorry, I'm rushing, I'm out of time. So let me just make the main claim, and maybe I can say a bit more next time. So here you have a broken symmetry when S is negative, and you're either on this side or this side of this effective potential. This is just like here. On this side, you have no broken symmetry, and that's like here. Now here I have this quasiparticle, which is this flip spin. That quasiparticle is just this oscillation over here, where there's a gap. And on this side, I have some small set of bubbles here. And that quasiparticle is just the Higgs particle, which is oscillations about this point. So and that also has a gap. So it's believed that this field theory not only describes the two phases, but now this is a field theory I can open up the textbooks and also understand the phase transition. And this is the field theory that was studied by Wilson and Fisher, and we know it's a conformal field theory. And the punchline is, from that conformal field theory, we deduce that, in fact, at this point, G equals Gc, there are no quasiparticles. So it's a state of matter. It's really the first state of matter known, which has no quasiparticle excitations. And that follows from the structure of the conformal field theory in 2 + 1 dimension. In 1D, it's not true. 1D, there are quasiparticles, even at the critical point. Yeah, okay. You may have to go to some more complicated set of excitations, the fermionic excitations, or some. In the Luttinger liquid, there are bosonic excitations, which are quasiparticles. Here, as far as we know, there's no hidden integrability, there's no hidden duality, which will give you a set of quasiparticles. And that's what makes this critical point worth study. Now, there's some not so recent and also recent Rydberg atom experiments studying this critical point, but I won't say much about that. Okay, thanks.